Sir, Madam, hello everybody. Before we begin, let me introduce myself briefly. I am Amal and I am a PhD student. Today I'm going to be talking about our work entitled CAD System Engineering Interoperability by Enriching CAD Database with Functional Information. So, I will begin with introducing the general topic, then I will present some related works, and I will continue by explaining the proposed approach, then the implementation and validation to finish with the conclusion. CAD software presents a revolution in modern industry. There are two types, commercial like SolidWorks and CATIA, and open source like FreeCAD. Open source CAD software is the trend of today's developers, because they don't need licensing code, just install them from the internet and enjoy. CAD software are motorized with geometric modeling kernel, which generates the geometrical part information. When specifying the design solution, the designer always thinks in terms of function to be satisfied and parts interaction into an assembly and how they are mounted together. However, this information are lost once the design solution is validated, and we still need them for the requirement verification and validation doing by the system engineering. Okay, that covers the main problem. I'd like now to move on and discuss some related works. I'll begin with assembly sequence planning, where Belhaj are interested with implementing a method that generates the assembly sequence planning integrated in a CAD system such as SolidWorks, which extracted data from the CAD model and research automatically the assembly sequences, but they are working on commercial software and they eliminate the standard component during the calculation. Let's move on to another work where Belhaj have proposed an approach integrated in CAD system which aims to identify subassemblies, then disassembly sequence of the subassemblies of a mechanical system. The subassemblies are automatically generated to identify disassembly sequences. However, the subassemblies identification is done from the geometric models, so there is no functional information. Let's finish with the CAD data extraction, where Guta et al. Have proposed a tool named CADLab to collect and extract data from the assembly CAD model. This work gives a data extraction into different platforms like Excel and MATLAB, and it gives a great time saving with a platform integrated directly in a CAD software. However, we don't have any idea about part functions and fit type between them. So, how can we resolve this weakness? To resolve this problem, an approach is proposed, which is the development of a CAD tool integrated with an open source CAD software to enrich its database with the part function during their creation, CADPF, and the fit type for certain assembly constraint CADACT. So, CADPF will be integrated in the part model to give a part enriched with functional information. For example, this shaft is used to transmit the movement between two other parts. Here, we add the part function to avoid the problem of manual requirements verification between the industry and her subcontractors, design industry, and generates automatically the allocation matrix which represents every part in an assembly with its function. Let's move to the CADACT, which will be integrated into the assembly model to give an assembly enriched with functional information. For example, in this assembly there is three parts, a hub, shaft, and a bearing. We suppose that is a rotating shaft, so the bearing is mounted with a tight fit on the shaft and with a loose fit on the hub. It will be so useful when we find this information in the assembly database. First, to give more precision to the manufacturing industries, and second, to generate the fit matrix, which is so useful in the subassemblies identification. Okay, that's covered the idea of the approach. Let's move on more detail. How can we make this approach real? We search and we find. The data processing implementation of the CAD-PF and the CADAC tool are carried out using the FreeCAD software. The APE function of the CAD system are handled with Python programming language. The CAD system tool for the database enrichment with functional information is realized with the interactions between Python and FreeCAD. The idea is realized correctly, and this is the graphic user interfaces. First, the CAD-PF interface is integrated in the part design module, and it's composed of the part name, number, function, and standard library. It imports the data introduced by the user and adds them to the part properties. Let's move to the CADAC interface, which is displayed when a circular or a coaxial constraint between two parts is selected. It's used to specify the fit type and the tolerance interval between them. Now our interfaces are ready to use, so we need to validate them. The validation example is a wet machine, which is the key of the Industrial Revolution in 1763. Using the main poly to validate the CAD-PF, and it works correctly. The main poly function is turn another part or another system. His number is 6. These information are introduced by the designer and saved with the part properties. So, the introduced information are in the left table. The database extraction code is executed to give the information on the right, where the CAD-PF information are highlighted. And they are the same information introduced in the beginning. We move to the CADAC validation. The constraint between the bearing support 5 and the plane bearing 22 is a tight fit with a P7 tolerance. The data extraction code gives these results, where we find the underlined informations in the assembly database. As you see here, the first line contains the fit type introduced, which is a tight fit, in the bearing support 5 database. And it's the same in the second paragraph, which presents the plane bearing 22 database. Also, the tolerance interval in the 8th line in the first paragraph and the 8th in the second, which is a P7 tolerance. So, our informations are correctly saved. Also, between the plane bearing 22 and the crankshaft 31 is a loose fit with a J6 tolerance. The data extraction code is executed and gives this information, where we find in the first line, which is underlined, the fit type, which is a loose fit in the plane bearing 22 database. Also, the same in the third line underlined, which presents line of the crankshaft database. As the same, the tolerance interval is presented in the two parts database. So, now we can say that these interfaces works correctly. Let's resume this work. The CAD-PF information are executable, so we can edit them anytime. They are used only for parts. It will be a good idea if we try to do the same for subassemblies. And they are also enriched with a standard library which contains the standard parts like bearings with their functions predefined. Also, the CADAC information are executable. and they are used only for coaxial and circular constraints. So it's used only for two revoluted parts, and it's enriched with the tolerance interval specification, which gives the assembly more precision. Finally, we end this presentation with the conclusion. This work is elaborated using the graphic modeling language SysML, FreeCAD for the implementation, and Python for coding. Using these softwares, we can enrich the CAD system database with functional information and preparing for the automatic generation of the allocation matrix, which is very important to verify and validate the system engineering requirements, and preparing for the automatic generation of the fit matrix, which is vital for subassembly identification. After this work, our perspectives are the automatic generation of the allocation matrix and the fit matrix, and the comparative study will be done to compare these results with other results in terms of time saving and use simplicity. By the end, thanks a lot for your attention.